these went pretty well. If you haven't seen, corrections are a thing. Submitting corrections. If you look in World Class in the announcements, there is a detailed description of what I need from you to get those corrections in. Oh, geez, let's do these while I'm here. You can recoup 50% of what you lost, except on things you've only lost a point on. Cause come on. If you usually the stuff I took a point off for, I gave you the answer for. It was a very small thing. So yeah, check that through. First, make sure that my bookkeeping is okay. In that what I have taken off the 100 points this is worth is what should be taken off. If I didn't take off enough, you don't have to tell me that. That's my problem. If I didn't take off anything, damn good job. And happy to talk about any of that, but I'd kind of prefer to do it in private if there's something you're concerned about, because I don't want to give solutions out yet until after all corrections are in, and there's folks who definitely going to want to submit corrections and get back those points. And I'll release that. I think they are due Wednesday by like 2 p.m. in the door outside my office. If you need more time for some reason, please let me know, but I'm not sure I'm gonna be here after Wednesday for a long time. So we'll see. I think I might come in on Thursday just to see what's up and see if anybody needs anything, and I don't know, put on a good show, I guess, more than anything. So, is this all looking like what you'd expect? Everything looking okay? Yeah, good, cool. So, not a lot of folks have started on the current homework. One person I think might be close to done. Is anybody actually done? Yeah, so you're really close to done. You are freaking done. Cool. So I want to talk today about a little bit more, but I really want to emphasize, please try to work little bits. Try to get up on this stuff because it's going to bite you if you're not building slowly. These ideas are small at the beginning and then become much bigger. So we really want to keep on top of things. Are there any questions on that homework? Anything I can do? Anna has no questions. We're good? Okay, cool. So let's get rolling. I'm actually going to want to use Desmos today, so I should have got this open. Just give me a second here, please. But there will be a new MyOpenMath that opens today. And I kind of want to set the due date on the past one. I moved the due date on this last one from tomorrow to Wednesday. And I would like this new one to maybe be done by the end of the class on Wednesday, and we'll spend time in class working on stuff on Wednesday. But things are about to get very, very interesting. So let's get rolling. And Anna, would you mind just double checking to see if I'm rolling over there, please?
Yep, you are.
Cool, awesome. Thank you, my friend. Beautiful. Okay, so let's see. What are my notes for myself? Yep. We talked about average rate of change. There's no calculus in this yet. The calculus comes today. Today we begin entering pretty much a new world, a very different set of ideas that stem from this, but then become really amazing. So average rate of change, if I've got a function, let's just do a quick review. If I've got y and x, I've got some graph, y equals f of x, and I want to find the average change over an interval. I find the change in height over that interval. So I'm going to find f of b minus f of a over the change in x. And you could do b minus a here. And that is, using this notation, the change in f over the change in the x coordinate. So this is the average rate of change over the interval. We want to talk about where this happens, over the interval a, b. Does this sound right? Sound familiar? Cool. Very, very good. So, yeah, that's what the first homework is pretty much all about. That's the heart of it. But I want to talk about something we started hinting at last time. Let me get a new graph up here. And I want to reframe the interval we're looking at. And we're going to work some problems together. So let's say I have y equals x squared. And I think this is exactly where we left off. The point 3 gives me an output of 9. And I'm going to scoot over. So I want to introduce this new notation that's really fundamental. Same thing as over here, but done in a slightly different way. I'm going to move over h units. So the next point is 3 plus h. That's my new input. And I go up here, and I ask what comes out, and that is 3 plus h squared. And I'm going to rewrite this one as 3 squared also, just to emphasize the rhythm going on underneath. So let me stop for a second, because it's Monday. And we had a weekend, and it takes a while to get cooking again. Is this looking okay? Any questions? Anything need clarification here at all? So I'm gonna do something I haven't done yet, and that is connect the 2 points on the ends here. So I'm gonna draw a straight line right through those things. Imagine it is, because it's not. But this draw a straight line right through these 2 points. Let's pretend I'm gonna hack him. Make it like that. This is called a secant line. And a secant line is a line between 2 points on a shape or a curve. So secant line is a line between, 2 points on a curve. Oh, don't worry about it, Katya. It's cool. I'm hoping to God Mace comes anyway. So, yeah, I'm hoping you show up, Mace. You watching this, Mace? We're missing you. We know you're gone. So that's a secant line. Now, what I did in the little demo that we did last time was take this point and start moving it closer to this one. Does that sound vaguely familiar? Taking this 3 plus h and making h less and less. So right here, what we have is the average rate of change. We can do this right now. Average rate of change over 3 to 3 plus h. And the way I've drawn this picture, h is a positive number. H could also have been a negative number, and I would have drawn the picture with this point over here, but then this would be the leftmost and this would be the rightmost. Nothing is lost by doing it the way we're doing it here. So average rate of change over this is delta f over delta x. And actually, let's change this one more time. Let's change this to delta y. Changing the y, the vertical component, over the horizontal component is, and I'll write this out, f of the right endpoint minus f of the left over the change. What is the change here? What is the delta x? What will that be?
H?
Yeah, it's h, right? And we could see that, even if we didn't see that obviously, we could take 3 plus h minus h, minus 3, the left point, and we would see that this change in x is just h units. And that could be positive or negative, like I said. So let's go now, what is f? This is f of x, right here. So this is going to be literally just that point minus that point. So it's going to be 3 plus h squared minus 3 squared over h. Stop there for a second. I got your exam for you, got the answer. So yeah, let's just talk after class. Or we'll just do it. Yeah. I don't think you're going to need to do corrections. Quite well. Thank you. A pleasure. Sound good so far? Making sense what's on the board here? Yeah? So now, check this out. I've got a formula, and no matter what h is, I can compute the average rate of change. So you tell me, h is 1 unit. I can just plug h is 1 in here and know exactly what this average rate of change is. What if I started letting h get smaller and smaller? So think about what happens to this picture. Let's see if I can do a little bit of a movie here. Boy, that is one sad-ass parabola. That is bad. So I've got 3 plus, here's the 3. This is a little bit better. And then here's the other point. And I'm looking at these secant lines. And I'm gonna let this right point get closer. So I'm gonna let h shrink in size. What is happening here to the lines? What happens at the moment? What does the secant line do when h becomes 0? When these 2 points merge together, what does the picture look like?
A horizontal line?
Not necessarily horizontal. So that I can see why you'd say that. So check this out. Actually, let's let Desmos help us see this, because I think this is something really worth taking a look at. All right, so pop you on, and I put this app or some version of it up in World Class in the content area, Desmos, under that little folder. So I'm just gonna do Desmos rate, instantaneous rate of change. That's splendid. And let's make this the function we're actually looking at. So we're looking at y equals x squared. Beauty. Cool, and let's back out a little bit. And let's make our leftmost point 3. This thing kind of sucks a little bit. Can I move that point? I don't like this one, sorry. This is a lousy one. Whoever built this just did not do a great job. Sure, this might be better. Can I just move the, oh my God, what is those, like, too messy. I could go to World Class and find my buddy there, but I'll have to log in and do all the Regis nonsense. Come on. No, I just keep looking at the same ones. I got a desperate text message from my mom this morning, or yesterday, saying, help, all the pictures I keep trying to upload to Instagram keep going to Facebook. That's probably what you feel like watching me do this stuff. Sometimes I feel like grandpa up here. You just want to come up and grab the thing from me. Well, just like, look out, Gramps. Wait, let me show you something. Okay, I'm just gonna go to this one and hack it. So I've got x squared, and I don't need that. And then we want the point 3, comma f of 3. Cool, all right, this is starting to tweak. And then, what is that now? Oh, that's the line. Okay, cool. So then minus 3 plus 3. Okay, I see what's going on here now. And so this then is the h, the other point. It doesn't seem to be going through it, so I have to tweak this one too, and then we'll be good to roll. Bruh, why are you not like going through that point? Okay. Oh, because this isn't really the damn thing that I want. I apologize. I should just go, let me just go to world class, sorry. I have a nice app for us to use. You can follow along if you want to go to world class. Oh my God, I actually logged in. This is great. I didn't have to go through the rigmarole. So I can show you this content. Instantaneous rate of change. Huzzah! Freaking hell. All right. Literally pretty much the same thing we were just looking at, but like actually working. So this is good. So here we've got x squared. We see our 2 points. Let's just work from 2. I don't want to start tweaking this thing. Let's do this, but the leftmost point is at 2. Here, I'm going to tweak this really quick. 2 plus h, 2 squared is 4, and 2 plus h. There. So this average rate of change, this is all just going to be 2 and 2, and that's still the same. So we kind of see that right here. We see the right end minus the left end vertically over the change horizontally. So now watch what happens. As I move this left point, I'm going to zoom in here so we can really see this. I let h shrink. So notice secant line, secant line, secant line. What happens when I get right in there? So now h is super small. What is happening? The line's not going horizontal, right, Jack?
Yeah.
Yeah, what is it actually doing? Well, it kind of disappears at the end because when h is 0, I'm dividing by 0. Does anybody know the word for a line that touches at one point? What do you call that kind of line? We have a secant line. That's a tangent line. So tangent means I just brush the curve at one point. So what happens here is that as these 2 points come together, this secant line becomes a tangent line. And a tangent line, like I said, just touches at one point, but it also gives us something else. So let's talk about this. Let me get this picture up. Here's 2. And what happens the moment h becomes 0, which we can't actually compute with that formula, we have a tangent line. And this line represents the instantaneous rate of change. So its slope equals the instantaneous rate of change. This is what I was talking about on Wednesday. When you're driving your car, you got your foot on the accelerator, giving it gas, and it's fluctuating. You're watching that needle move back and forth, and it's never really constant, unless you're in cruise control or something like that. But if you're doing it manually, you're just seeing that needle move back and forth. So when you read it at an instant, what does it say? 54 miles an hour. That's only for the second I look at it, and then it's going up again or down again. So what we're looking for is how to understand instantaneous rate of change instead of average rate of change. What is the rate of change at a point as opposed to over an interval? And what we get here is a problem because as h shrinks to 0, you see it barfs. Because in this formula, let me put the formula back up. So we had 2 plus h squared minus 2 squared over h. Can't let h equal 0. So how do we get to that instantaneous moment? And the answer is, I'm first going to do a little algebra here. Could you help me out, friends? Could you just take a minute and simplify the top and then simplify the whole thing? Something nice will happen when you simplify the top. FOIL. Subtract that off and then divide by h. Let's see, let's get together and agree on this. Get this guy out here. I'm gonna do a little front light just because I'm worried about the recording. Yes. Is that just looking kosher? I took the 2, squared it out, just replaced it with a 4. Is the FOIL okay for everybody? The 2 plus h squared? Cool. Cancel, cancel. Those 4's cancel. I'm left with 4h plus h squared. I'll proceed carefully. What could happen next? What could I do here?
Factor out an h.
Factor out an h. There's an h in common here. So I pull out an h. So this is factor out h. You're going to have to do this a number of times for the homework and stuff. So let's just make sure it's making sense and resonating. And then I divide by h. And now, good shit. Now I can cancel that h. Always factor before you cancel it out, just for safety's sake. Things can get weird. If you're really good with algebra, you're okay, but still be safe. So now, look at what we've got. That formula is beautiful. You can do that in your head. If I tell you, ask, what's the average rate of change when h is 1? What is that? What's the average rate of change when h is 1 unit? 5, just plug it in, right? What's the average rate of change when h is 0? 4. So now I can replace h with 0. Now we can let h equal 0, and what we get, 4. And this is equal to the slope of the tangent line at 2 tangent line at x equals 2, and it is equal to the instantaneous, and I want all of us to understand these two things are the same. And there's one more thing we're gonna get to very shortly, probably on Wednesday, that is equivalent to these two. Instantaneous rate of change at x equals 2. So the things I just want you to take away from this, friends, right now is slope of the tangent line is instantaneous rate of change. And think about that average rate of change. We're just doing the same computation over and over again until we're just at a moment. And then we're good to go. So, I'm gonna clean up here. Let me know if there's anything there that you would like to ask about or talk about. Seem okay so far? All right, cool. So let me put a little bit of summary up here, and that leads us into the next thing we're going to chat about. So we let h become smaller and smaller in magnitude. This is the process of taking a limit. This is probably one of the hardest conceptual things that calc students deal with. So we've got we're not going to do it in the most rigorous and painful way, but we are going to understand what this means, the process of taking a limit. And this is where calculus starts, right here, the idea of a limit. So, let me notation. We have this f of 2 plus h minus f of 2 over h. We want to describe to someone, hey, can you please let h get smaller and smaller, get as close to 0 as possible? We use this notation, that is LIM, so I put a LIM out front, that stands for limit, and then I tell what I'm getting closer to. H goes to 0. So when I see this, what I know is we want to study the value of this quantity as h approaches 0. Let's just use that word now. Approaches 0. But here's the key. But is not 0. So this idea of a limit is never about what happens at a point. It's about what happens near a point. I'm going to write that up here. Limits are all about what happens near a point. Not at a point. And so this is why it's a big conceptual shift. Not at a point. And the only way to really understand this is to do some practice. So right off, let me start with a picture and show you what I'm talking about, and then we'll do some practice together. So let's say I've got some weird function. This one's gonna look really weird. I'm gonna put a hole right there. I'm gonna keep going, and I'll just stop kind of with that. Let's say that that's 2, and that height is 4, so we're kind of like at that x squared thing, even though this isn't a parabola, clearly. But the function jumps up right here. Just at the single point 2, we've got a different value, and that looks like maybe 8 or something like that. Does this picture make sense? So this is y equals f of x. And let's make a note, if this doesn't make sense to you, you might want to make a little note. The function has a hole in it. The function graph has a hole in it at 2, 4. And the value of the function at that point is 8. So, for example, if I asked you, what is f of 2.0001 approximately? That means that I'm just a little bit to the right of 2. So I'm right here. I'm still at about 4. It's about 4. And f of just a little bit to the left, 1.999. That's approximately 4. But f of 2 is 8. It was a big jump right at that point. Let me stop. Questions? Does this need any other different words? No? Okay. So these two facts right here, and more importantly, the thing I'm about to show you. If you want to take a limit at a point, get my little couch. Kill myself practically. If you want to take a limit at a point, say 2, take your fingers and follow the graph toward that point from both sides. The value your fingers are approaching, the height output your fingers are approaching as you get close to that point is the limit. That's really key. So always think about coming in from the right side, riding on the curve, riding on the curve. How high am I as I come in from this side? How high on this side? If those two things match, doesn't matter what happens at the point, doesn't even need to be defined. We have a limit. So we're going to write this up now. We can actually say something about this picture. Here, the limit as x, so this is a little different, approaches 2 of this function. So as x gets close to 2, but not at 2. I don't care what happens at 2, near 2. So this is x super near 2. What is the value of f when that happens? And the answer is 4. And f of 2, the actual point, is actually 8. This is different, right? This is not normal. This is not the math that you do leading up to this class. So let's do some problems together. Let's make this happen. Let me do one more example, and then we can talk about it. A limit sometimes there's not an answer, and we say that a limit doesn't exist. So let me put a little note here. A limit, or how about this? We'll say limit as x approaches c of f of x exists and equals L if f of x gets closer to L as x is when x is near C. So the picture here I'm talking about is this. Here's my y equals f of x. Let's just put a little hole there to make things look weird. Here's x equals c. Here's L. And what I'm saying here is mirrored in this picture, that as I approach from this side on the graph, the output comes to L. As I approach to this, from this side, the output approaches L. Gotta be the same thing. So what happens, how does a limit not exist? And it's when I approach different values from different sides. My fingers cannot meet. For us, that's the extent of it. There's some other weird situations, but they involve trigonometry, and we don't do that in here, so it's all good. So a limit does not exist if, as we approach from each side, we get different values. So I'm going to show you this. Once you see this picture, you'll know exactly what this means. Different values. So let's get another function out here. Here's good old that starting out, and then it jumps. It looks like this. So here's the point, x equals c. This is y equals f of x. As I ride toward x equals c on the curve from the right, I approach this value. So this value is approached from the right. The word approach is a super calculus-y word. From the right. And this one, this value here, so this is the value I'm talking about. What is this value here? This value is approached from the left. So this limit does not exist. So if I asked you, find this. Limit as x approaches c of this function, you would say does not exist. And you would say because the left and right limits are not equal. Different value from the right than from the left. So now, could we please check out in our texts, exercises 2.2, that's on page 83. And I'll put them up here, but there's graphs and stuff that we're gonna wanna look at. And I think we should just start with problem 1. Use the graph to determine these things. You might get it wrong, it's cool, we're here to figure out what is happening. So could you please take some time on problem 1 and just work through those 4 limits that you're asked to compute. And I'll come around. Actually, maybe I'll get the graph up here so that we can talk about it together, and then I'll come see what's up. Add a few questions to it. There's lots of mistakes that you might make along the way because that's the mistakes people make. There's a lot of classic things that people do, and we're going to try to shake them all out. I'm going to add a few questions to this. I'm going to add a E and F. I'm trying to get these guys written up here. So for A. I'm going to kind of call on folks about this just to see what you're thinking. Oh, that's a 1, isn't it? Okay, that's a 1. Oh, I see. Well, that all makes sense. Then, what I would like to ask you are these also. What is f of 2? What is f of 3? Yay, calculus starts. Oh, sorry, yeah. It was page 83. Let me know if it's not popping up for you. Let you use my copy. Let's have to bump it off you. How's this feeling? Oh, look at you typing shit up. Do you always type notes? Wow. That's impressive. Yeah, that's impressive. So let's see what we got here. So I forget what was it? That was as we approach 1. So 2, beautiful. As we approach 2. You got this. You got this. Awesome. Well done. Nice. With 80, I think I said 83. I almost forgot to. I'll come check on you. Let's. Oh yeah, thank you. That's good. How's it going? Is it? Let's take a look. I honestly can't even remember from 5 seconds ago. And I told Laurel I should was gonna write. So the first one was 2. Yep. And then the next Okay, so as you ride along the right and you come over 3, what is the output approaching along this branch? The output, what is the y coordinate approaching as I move along that from this side? It is 2, I agree, but from the left, what do I approach? Yeah. Yeah, so since those aren't the same, then D and E. Yes, yeah, that's cool. Yeah, you got it. That's cool. How's it going, Lisa? Is this making sense? Maybe. Cool. Yeah, right. Yeah. So let's take a look here. So what did you get for C here? You got 2. So on C, we're looking at the limit as x approaches 3. So tell me how you came up with 2. Yeah. Yeah, and that's definitely as you ride in from the right. So as you ride on the curve from the right to right above 3, your output approaches 2. But as you ride on the left, getting closer to 3, your output approaches -1. So since those 2, my fingers wouldn't come together if I traced from left to right. So the limit does not exist at that point. Yeah, your fingers have to meet. I should have said that, but as you trace the graph over towards the point you're interested in, your fingers need to meet, and if they can't meet, the limit doesn't exist. So you say it does not exist, and you can abbreviate that D and E.
Okay.
Yeah. Does that make sense?
Yeah.
Cool. Mr. Jack here. Is this sounding good to you?
Yeah.
Cool. Yep. And so you see why that's the case?
Yeah.
Yeah. And what was this? Yeah, that all looks beautiful. And then what about those E and F? What do you think about?
Oh,
That's okay. It's okay. We can probably do them together. What's the other 2?
2. Oh, what is the actual? Okay, F2 is 2.
Solid.
F3 is 1.
Solid. Yeah, absolutely. Good. Good.
Yeah.
Yay, people working together. We're all so spread out that we can't, I love this, yay. We can always work together. This is good. Maybe I should coerce you into this. Okay, cool, so we'll go through. This is looking good. So the thing I said to Louisa was really the thing I should have said to us all, is that if you're interested in taking a limit at a point, it's always with respect to the x coordinate. So you're looking at a vertical strip where you're taking the limit, just that slice. Do my fingers approach each other as I ride the curve toward that x coordinate? And if they do, then the height your fingers meet at, the height over here, is the limit. If your fingers do not meet, the limit does not exist. You've got to have the same thing from the right as you do from the left. So, on 1, the limit as x approaches 1 is equal to 2. And everybody got that? We're all in agreement on that. Awesome. And then B, the limit as x approaches 2 is 1, because my fingers approach this height of 1 from the right and from the left. So this is a 1. There's a big hole right there, and that's not the value of the function. F of 2 is this point right here. It's 2. It's just that dot. Where's that dot at? Limits have nothing to do with points. They are in neighborhoods of points, nearness. And then what's our next one? Limit as x approaches 3. On that one, that's the big fingers never could meet. Right in on this one, as I approach from the right, I go to 2. As I approach from the left, I go to -1. So for this does not exist. And Louisa said, what do I write for that? So does not exist, you can abbreviate DNE, and you might even want to put a reason, because the limit from the left is not equal to the limit from the right. So we can actually, and we don't really do it in this class, but we can have a right-hand limit and left-hand limits. And it's nice to have that language to explain why you're saying this. Limit as x approaches 4, 1. There's a hole there, it doesn't matter. The output approaches 1 as my fingers ride in, and the fingers definitely meet. So this is 1. And then f of 3 is that point right in the middle. What is the output when 3 is your x value? And the answer is 1. How does this feel? I got a thumbs up, yeah. We're gonna do a few more. Now I want to toss in an idea. And then we're gonna use it on the next one. A function is continuous at a point x equals c if a certain thing happens, and it's really 3 things, but we're going to write it as 1 first. If the limit as I approach that point is equal to the value of the function at that point. Okay, so let's talk about what does this mean right here. This part, to even say that the limit, well, here, let me write this in outline form. This is 3 conditions in 1. And it's hard to see that until you get told exactly how they're all sitting there. The first one is the limit at x, this limit exists because I'm saying it's equal to something, because we say it equals something. We're not saying DNE does not exist. We're saying it's this number right here. So the limit exists, and what does that mean? That means, without anything else yet, that at C, I have at least this going on. That the limit from the right is the limit from the left, and they both approach the same output. So the limit exists. I'm not ships passing in the night. 2, writing this instantly says F is defined at C. Look over here. F is not defined at 4 here. So F of 4 doesn't exist, is not defined. I don't know what it's not anything. But the minute I say this is equal to something else, this means it is defined there. So writing f of c means f is defined at c. There's no hole there. There's not a hole or an asymptote. So this is no hole, no asymptote. And then the third thing. So check this out. Let's come over here. Look at 2 here. Right here at 2. The limit exists at 2, because when I write in from the left and when I write in from the right, we get an output of 1. So my fingers approach 1. F is defined at 2, but it's not the value I get from the limit. Do you see this? Check it out. So as I approach from the left and the right, I get a 1 is the height I approach. The function is not 1 at that point. So let's just take a little note right here that in this case, the limit is not the same as the value at that point. At the point. So this third condition says that the limit is equal to the value of the function at that point. So let me write that up here. 3 is the limit at c, which we know exists because we wrote it equals something, is equal to the function value at that point. So what this means is there's no holes, so no hole, here, let's actually write this here. Yeah, I already wrote that. No hole or asymptote. And the hole here, if there was one, is filled in. These 3 conditions keep you from having this, or this, or this. Look at this one. Limit exists, function's not defined there. Got a hole. Limit does not exist. That's a big mess. That's a big jump. Here, limit exists, but the hole isn't filled right. So continuity is exactly kind of what you intuitively think of. Continuous means I can move without a break. A continuous function is a graph that has no holes or jumps in it. And these conditions, this condition right here, this just says mathematically what I'm saying here. So let me just kind of put it in easy to understand terms. A continuous function has no holes, asymptotes, and all limits exist. Or jumps. No holes, asymptotes, or jumps. And then we're good to go. And so, nice term. Easy to understand intuitively. This starts to get a little out there. Could we please turn our attention to problem 7 on page 84? So here it's asking, where does continuity get messed up? And we're just going to find the points where this isn't true. So in other words, go through left to right and figure out, where is there a hole or a jump or a hole that isn't filled properly? And you just list off the x coordinates. That's the easiest way. I guess that's like an asymptote on the left side of 3. It looks a little dicey to me. Discontinuity is the opposite of continuity. Discontinuous. Doing good on this, Lorelai?
I think so.
Yeah, awesome. Katya, feeling good? I saw that. Is this working for you, Lisa? Yeah, yeah. Mr. Jack probably just give me that sweet shirt.
Thank you.
What is it? Oh, nice.
Zach Bryan.
Oh, cool. Nice. And always kind of work left to right just as a nice systematic thing, lesser to more. what's the first point of discontinuity?
The first one, I don't know if this red is 0, 1, where it goes out like that.
Oh, I'm so glad you asked. That, there's no hole there. That's a great question. It's going to turn out to be something, it's not something else that we haven't talked about yet, but I like that you saw that. So Hannah was looking here, and notice how that's sharp there? There's a sharp point. That's going to be a thing we call not differentiable, not smooth. So Hannah, you're already kind of picking up on some more heavy concepts here, but it is continuous.
Okay, then 3.
And then, so 3?
Yeah.
Okay, cool. We got x equals 3. Lorelai, do you see any other points of discontinuity?
4.
Beautiful. Big jumps, right? This one, big jump, jump. Luisa, you got any more for me?
1.
Beautiful. Big hole right there, right? So there's actually, it's not even defined there. So let's make a few notes. Thank you. And I think that's it. 1, 3, and 4. So here, the function's not defined. You want to be able to give some kind of loose reason. It doesn't have to be super mathy, just the basics in English. 3, we have a jump, maybe an asymptote on the left. That's weird shit. It's a jump no matter what. So we have jumps at 3 and 4. We can't be continuous there. Let's do one more example, because I want you to be able to start on your homework. So let me stop here. Does this feel okay? Got this, cool. It's a very different thing to do in math, right? It's a very qualitative feeling kind of thing to do. There's no computation to do. Let me grab one of the problems off page 84. So some of the problems you're going to have look like this. This is number 5. It says evaluate the limit as x goes to 1 of x cubed plus 3x plus 3 over x minus 2. Now I'm going to tell you the great secret of limits. This is good shit. If I ask you to find this, I guess you could plot this out. You could go to Desmos and make a plot of this, but you don't need to. Step 1, when it says evaluate any limit, step 1 is, can I plug the limit in and not have division by 0? And if you can, the number you get out is your limit. If so, the number we get out equals the limit. Basically because that function is continuous then at that point. If it's continuous, the limit is the value at that point. So for this one, I'm going to try that. Just plug and chug is the way I like to say it. Plug and chug. That's step 1. So plug that in, and what do you get? And you can eyeball that you're not going to get division by 0. So what do we get? 7 over -1. I got -7. Let's make sure that we all get that. Maybe I screwed up my math. So now let's look at B, where it's going to get interesting. Where would be a weird spot, a troublesome spot to take the limit? I don't think I wrote that right. Did I copy that problem properly? Yeah, I did. I hate it, but I did. where would be a trouble spot? What x value might be trouble for us? Where would I get division by 0?
2.
2. There you go. Right, so you look at this and you say, everything looks cool except if x was 2. So in question B, they say, what about this one? Limit as x approaches 2 of x cubed plus 3x plus 3 over x minus 2. Same thing. We try plug and chug because this is the first thing we always try. So plug and chug. We're just going to get plugged. There will be no chug. So when we plug and chug on top, we get 2 cubed plus 3 times 2 plus 3 over 0. Bad shit. What is the top equal to? Because we kind of want to know. What's the top equal to?
17.
17. That's 17 over 0. Notice that the top isn't 0. So here we have a non-zero thing over 0. That's after plug and chug. This means the limit doesn't exist. There's some kind of asymptote, some kind of explosion to infinity or negative infinity here. So this means the limit does not exist. Division by 0 is good enough. But division by 0 isn't always a problem for us. So that's the last thing I want to talk about. And we'll call it a day. Wednesday is pretty much going to be a work day. Come on in and work and talk about these things because I've got a pretty good problem set. Let's do one more. I'm going to make this one up. Limit as x approaches 2. I want the bottom to still be x minus 2, but I'm going to make the top x squared minus x minus 6. Yeah. X squared plus x minus 6. All right, so let's try this. Plug and chug, right? You give this, if you're not trying that, yeah, this isn't gonna go. This is gonna save your ass so many times. So we plug, again, 2 squared plus 2 minus 6 over 2 minus 2. What do I got?
Zero on top.
I got 0 over 0 now. Yeah, so this is 0 over 0. Surprisingly, that's good news. This is good shit. So if we get 0 over 0, there is hope. And the hope comes from factoring the top and hoping to God it cancels with the bottom. So if you get 0, 0, step 2 is to factor everything. Here, there's nothing to factor in the bottom. And cancel what can be canceled. So could you do that for me really quick, please? Could you just take a look and just do a little factoring work on that? And I'll write it down here. Let's just do the factoring together. What does the top become? Yeah, Jack, what'd you get?
X minus 2x plus 3.
Beautiful, thank you, sir. Let's give everybody a second here. Is this looking okay? Yeah? I see a lovely cancellation. So we're gonna cancel and attempt the limit again. So this is the limit as x approaches 2 of just x plus 3. Holy shit, that's great. Plug and chug gives me what? Now I go back to plug and chug. Plug equals what? Lorelai, what do I get?
5.
Beautiful, thank you, ma'am. I get 5, and that's the chug. That's my limit. And so that is the answer to the original problem. We just use a little algebra to get rid of the 0 over 0, and then chug again. So here I can just come up here and say that is 5. That's all we're gonna do with limits for a little bit. So today, limits and continuity. Is this feeling okay? Cool. So, and also, here's a little word of de-stressing. We're just going to talk about limits for a little bit because they are important in understanding the main thing we're interested in this semester, and that is the derivative. This is what we hope to get to. God, we'll get to this. If things go well, we will talk about the reverse of this. So in the same way that multiplication and division are inverses of each other, addition and subtraction are inverses of each other, we're going to talk about this thing called the derivative, mostly this. If we have time, the last few weeks of class, we will talk about its inverse, which is the integral. I hope we get there. I would like us to get there. I think we can do it. Honestly, like after spring break, boy, it's a downhill slide. It goes fast. So we'll do what we can. Like I told you at the beginning, last time this class ever runs, you have no classes afterwards that depend upon this information directly. So wherever we get to, that's where we get to. I don't care. I just want to get there safely and have everybody still in the cart. All right, my friends, thank you. So you got some homework. Please take a look at it before Wednesday. Know that Wednesday's just going to be a work day, so you can come in and work too. And cool. See y'all soon.